Good morning, students. Welcome to Microwave Engineering Laboratory. And today's experiment is measurement of impedance of a given load. Aim of the experiment is to measure unknown impedance of a given load. You have to consider two loads here. One is a matched load, and second one is movable short. By using these two, you have to find out the unknown impedance of a load. So the required apparatus is microwave source, isolator, frequency meter, and VSWR meter, variable attenuator, slotted line, tunable probe, waveguide stands, movable short, and matched termination. Next, let's coming to the setup bench which we are using in the laboratory. Microwave source is connected to the isolator is connected to the variable attenuator to frequency meter to slotted section to tunable probe to VSWR meter. Other side, matched load. Initially, you have to connect the detector mount to the slotted section and straight away calculate the powers. Okay. Then step number 2, remove the detector mount and connect the matched termination to the slotted section. Other side, tunable probe to the CRO and VSWR meter. So this is another combination. So by using this one, you have to calculate the impedance of a load. And case number 3, take off the matched load, connect the movable short, and repeat the same procedure, and you have to find out the impedance of a movable short. So these are the 3 ways. Coming to the observations, you have to find out the input voltage. I mean, whatever the voltage you have given, that is the input voltage. Beam voltage, that should be in between 230 to 240 volts. Rippler voltage, by rotating the rippler knob, you have to fix the maximum signal strength which appears on a CRO screen. And that voltage is a rippler voltage, which is in the reverse direction. So you have to keep the minus sign in front of the voltage. Then beam current, that should not exceed the 18 milliamps. Remember that one. It is a very important point. When the current is beyond the 18 milliamps, means when it is enter into the negative resistance region. Suppose if you use the gun diode, so it is a huge amount of powers, right, to use to generate the microwave energy. So obviously it will be like a burnout. So remember, so maintain beam current below 18 milliamps. Yeah, next one, observations. Coming to the observations, so you have to find out the distance as well as the power values. Okay, at a distance, what is the minimum power and what is the maximum power? Okay, so there are the combinations. You can go for the 4 to 5 readings. I mean, 4 minimum readings and 4 maximum readings, like that. And you have to take the differences also. I have given the observations here for to understanding purpose. You have to perform the experiment in the laboratory. You have to take the values like this. Okay, one side distance, on the other side there is a power. When you move the tunable probe on a slotted section, okay, it has a scale and it gives a value. When you moving at a particular distance, you have to see the signal strength on your CR screen. Is it maximum or minimum? So for the minimum power, what is the distance? Okay, at 10 centimeters, it gives the power value 59.7 dB, and that is a minimum. Okay, next you have still you keep on moving. So minimum signal goes to maximum, where you have to take the value, that is 11.4 centimeters, and the power is 59.3 dB, and that is a maximum reading. Okay, still move on. Then signal goes to again minimum, where you have to take the value, other value at 12.4 centimeter distance, 59.5 is a dB, I mean power, that is a minimum reading. Keep on move the tunable probe on a slotted section. Again, signal strength goes to the max, and that value is 14.2 centimeters, 59.7 power, and that is the maximum reading. Like that, you will get 4 minimum readings and 4 maximum readings. By checking the readings, so you have to find out the guided wavelength and standing wave ratio, reflection coefficient. Okay, see, so lambda g guided wavelength equal to 2 into d2 minus d1, the difference between the distances. So d1 and d2, here I have both values, I have taken the minimums only. Remember, either you have to consider the two maximum positions or two minimum positions. So here d2 and d1, first minimum position and second minimum position, the difference value lambda g equal to 2 into d2 minus d1, and the value is 4.8. And there is a relation, a standing wave ratio, which is equal to guided wavelength divided by pi into d2 minus d1. And we know the d2 and d1 values. By substituting the lambda g and d2 and d1 values, you will get 0.636 as a value for the standing wave ratio. After knowing the standing wave ratio, we know another relation, standing wave ratio equal to 1 plus reflection coefficient divided by 1 minus reflection coefficient. So by substituting the standing wave ratio value, we can find out the reflection coefficient. Here the reflection coefficient is 0.22. And another relation, reflection coefficient, which is equal to z minus z naught divided by z plus z naught. Here z naught is the characteristic impedance of the line and z is the unknown impedance value of the load. So reflection coefficient equal to z minus z naught divided by z plus z naught. We know the z naught value, characteristic impedance value. Here I have considered 50 ohms. By substituting the 50 and reflection coefficient value, then we can find out the unknown impedance value of the load. And that is z is equal to 78.2 ohms. So now take off the matched termination from the test bench. Okay, remove the matched termination and connect the mobile short and repeat the same procedure. For the mobile short, these are the distance values and power values. Here also I have given the two minimum and two maximum position values. By substituting maximum, here also take the either maximum or minimum. So I considered only the minimum value. So lambda c is equal to 2 into d2 minus d1, and it use the 4.2, and standing wave ratio is equal to 0.636. And there is a relation, standing wave ratio equal to 1 plus r by 1 minus r. R is the reflection coefficient, and that value is I have find out the 0.22. And there is another relation, reflection coefficient, which is equal to z minus z naught divided by z plus z naught. Z naught is the characteristic impedance of the line, and z is the impedance of the load. Right here, the load is mobile short. By substituting the r value and z naught value, I have considered that z naught value is 75. Okay, by substituting this value and final, the load of the impedance value for the mobile short is 117. Okay, 117 ohms. Let's see the Viva questions. Question number 1. What device is used to produce a gradual change in impedance at the end of the waveguide? Question number 2. When a waveguide is terminated in a resistive load, the load must be matched to what property of the waveguide? Question number 3. What is the primary purpose of the dummy load? Question number 4. The energy dissipated by a resistive load is most often in what form? Question number 5. What is the result of an abrupt change in the size, shape, or dielectric of a waveguide? Question number 6. A waveguide bend must have what minimum radius? Question number 7. What is the most common type of waveguide joint? Question number 8. What is the most likely cause of losses in a waveguide system? So these are the questions I have raised here. Try to answer this. Good morning, students. Welcome back to the microwave engineering laboratory, and today's experiment is measurement of impedance of a given load. Here there are two loads. So by connecting the matched termination and movable short to the slotted section, you have to find out the impedance value. So initially, step number 1, connect the detector mount to the slotted section and find out the powers. So before going to start, initially switch on the switch on the cooling fan, okay, then switch on the Klystron power supply. Make sure the voltage should be in between 230 to 240, okay. Then take the corresponding beam current, and that value it should not exceed the 18 milliamps, okay. Then by rotating the regular voltage knob in anti-clockwise direction, fix the maximum signal appears at CRO screen. See here, so it is a maximum signal. Now you have to calculate the power values. So by taking the amplitude value and apply 20 log of that voltage value, we can calculate the power. And another way, straight away by using the standing wave ratio meter, we can calculate the power values. Okay. Now, madam, remove the detector mount. Slowly remove the detector mount. Connect the tunable probe on a slotted section. Give me the tunable probe. Yeah. See here. So this is what the tunable probe. You have to fix the tunable probe on a slotted section, and it has a scale. So by moving the tunable probe on a scale, slotted section, then you have to check the power values as well as the voltage standing wave ratio. Connect the terminator now. Yeah, connect the load. SS tuner with a combination of load. There is a stand. అక్కడ ఉంది ఆ బెంచ్ తీసుకో. Let's check it here. So slotted section, SS tuner to the maxed load. Okay. Now release the SS tuner to minimum reflection position. Okay, don't apply any load, just leave it. And now calculate the standing wave ratios. Now move probe on a slotted section. Check the positions. So there is a minimum signal, 0. So this is what the one minimum position. Now maximum, and it goes to the again minimum. Okay, and now still move on maximum and minimum, like that. So you have to perform the experiment and you have to find out the minimum and maximum positions as well as the power and reflection coefficient values. So this is what the actually starting point. Okay, now here the first minimum value we used to call it like a D1. We can take the value here. There is a scale. Okay, by matching the scale we can take the value. Here it is a 9, so D1 is a 9. Okay, corresponding power as well as the reflection coefficient. Okay, so there are two ways. Initially we can find out the guided wavelength by using D1 and D2 values. So here it is a D1, right? Then go for the maximum and again minimum. This is a D2. By find out the D1 and D2 values, we can find out the guided wavelength. Lambda G equal to 2 into D2 minus D1. Okay, the formula for the guided wavelength, lambda G equal to 2 into D2 minus D1. So by find out the D2 and D1, we can find out the guided wavelength. So by knowing the guided wavelength, we can find out the SWR. SWR equal to lambda G divided by pi into d2 minus d1, then you can know the SWR value, and we know the formula SWR equal to 1 plus R by 1 minus R. Okay, so standing wave ratio equal to 1 plus R by 1 minus R. By substituting the standing wave ratio in the formula, we can find out the reflection coefficient. So if you know the reflection coefficient, you can find out the load value. So reflection coefficient equal to Z minus Z naught divided by Z plus Z naught. Here Z naught is the characteristic impedance and Z is the impedance value of the load, given load. So take the Z naught value as a 50 ohms and we can find out the Z. R value we know, Z naught value we know. Then simple substitute those values in the formula, you can find out the Z, characteristic, impedance of the given load. So this is how you have to perform the experiment. Okay, now step number 3, remove the matched termination and connect the movable short. Yeah. Now remove the load, and so here I have taken the here the load is movable short. So remove the movable short, connect the matched termination and repeat the same procedure. So you have to perform this experiment in 3 steps. Step number 1, connect the detector mount. Step number 1, initially connect the detector mount, find out the power. Okay, step number 1. Step number 2, connect the SS tuner with a combination of movable short to the slotted line. Keep it slotted line by moving the tunable probe on the slotted section. Find out the 2 minimum positions, because the signal varies minimum maximum to minimum, minimum to maximum, and again minimum maximum, like that. You can find the 4 to 5 readings. Take any 2 successive minimum positions named as a D1 and D2. We can find out the guided wavelength, lambda g equal to 2 into d2 minus d1. By knowing the minimum values, we can find out the guided wavelength, and we know the formula standing wave ratio equal to lambda g divided by pi into d2 minus d1. Okay, so guided wavelength, substitute the guided wavelength and d2 and d1 values, we can find out the reflection coefficient. Okay, standing wave ratio. By knowing the standing wave ratio, we can find out the reflection coefficient. Standing wave ratio equal to 1 plus R by 1 minus R. So you can find out the R value, reflection coefficient. By knowing the reflection coefficient value, we can find out the impedance of the given load. That means R equal to reflection coefficient equal to Z minus Z naught by Z plus Z naught. So Z naught is the characteristic impedance that consider as a 50 ohms. R value we know. By substituting R value and Z naught value, we can find out the impedance of a given load. So perform the experiment for the matched termination as well as a movable short. Okay, this is how you have to find out the voltage standing wave ratio as well as the impedance of a given load. Thank you so much. Hello students, today in laboratory we already done the experiment, measurement of impedance of a given load. The practical observations are beam voltage is 240 volts, beam current 16 milliamps, Rippler voltage is minus 201 volt. It is in reverse direction, right? That's why we have kept the minus sign here. So there are 2 cases we have seen in the laboratory for matched load, okay, and for movable short. Let's see, for matched load, the impedance value you have to calculate, and the distance and power values are, so when we move the tunable probe on a slotted section and we calculated the minimum distances values, right? That for 10 centimeters minus 59.7 dB power, and this is what the position number 1 or distance 1, that is minimum distance d1, the minimum distance d1. For the maximum, okay, when you move again, so 12.4 distance and the power is 59.3 dB, and this is what the maximum, okay. At the distance of 12.4 centimeters, 59.5 dB, and this is what the required minimum position, that named as D2. So position 1, minimum position 1, D1, position 2, D2. And the next maximum for 12.4 centimeters, it is 59.7 dB, maximum value. The required formulas for a guided wavelength lambda g equal to 2 into d2 minus d1. We know this d2 and d1. The position values right, minimum position values. Take a difference d2 minus d1 and you will get the value 4.8. Okay, 4.8 centimeters. The standing wave ratio, the formula is lambda g divided by pi into d2 minus d1, and we already know lambda g value. Substitute here, we will get the SWR value 0.636. And next, we know the relation standing wave ratio equal to 1 plus reflection coefficient divided by 1 minus reflection coefficient. So we know the value SWR. By substituting the SWR value here, okay, we will get the reflection coefficient is 0.22. By knowing the reflection coefficient, we can calculate the impedance value of a given load. So R equal to Z minus Z naught divided by Z plus Z naught. Here Z naught is the characteristic impedance value and Z is the impedance of a given load. So characteristic impedance value, here I have considered 50 ohms. Okay, and by substituting the 50 and R value, get the impedance of a given load. For matched termination or matched load, it is 78.2 ohms. Let's see. Let's calculate the impedance value for the movable shot by using the same formulas. And initially, find the minimum distances d1 and d2. Here, d1 value is 8.8 centimeters and d2 is 10.9 centimeters. Repeat the experiment same, okay. For first minimum, the distance is 8.8 centimeters and power is 52.1 dB. Next, when you move tunable probe on a slotted section, okay, then next maximum value at 9.2 centimeters, the power value is 46.2 dB. Still move on, then you will get minimum at 10.9 centimeters, that consider as a D2. And if you still move on tunable probe on a slotted section, then you will get the maximum at 1.3 centimeters and power value is 46.6 dB. And find out the lambda g. We know the formula lambda g equal to 2 into d2 minus d1. By substituting the values d1 and d2 value, you will get the lambda g is equal to 4.2 centimeters. Then SWR equal to, you know, right, the formula SWR equal to lambda g divided by pi into d2 minus d1. By substituting values, you get the value is 0.636. And another relation, SWR equal to 1 plus R by 1 minus R. By substituting the SWR value, you can find out the reflection coefficient is 0.22. And another relation, reflection coefficient equal to Z minus Z naught divided by Z plus Z naught. Here Z naught is the characteristic impedance value and Z is the impedance of a movable shot. Okay. Substitute Z naught is a 50 and R is a 0.22, then you will get Z is 117 ohms. So this is how you have to find out the impedance of a given load. So here we consider two loads. One is a matched load, load number 1. Okay, and this is the load number 2. So for these two loads, I have to find out the impedance value. For the first one, the answer is 78.2 ohms. For the mobile short, for second it is 117 ohms. Thank you so much.